So here's a sample problem from your textbook. This is chapter 7, problem number 8. It describes an ice block floating in a river. An ice block floating in a river is pushed through a displacement of the following. It describes D, the displacement, as being equal to 15 meters in the I-hat direction minus 12 meters in the J-hat direction. And it says it's along a straight embankment by rushing water, which exerts a force of 210 newtons in the I-hat direction minus 150 newtons in the J-hat direction. So that's a newton there on the block. And the question asks, how much work does the force do on the block during the displacement? So this is a displacement and a force that may look somewhat complicated, but these are simply constant quantities. It's just that they have a force and a displacement that happen to have components in both the I and J-hat directions. So what we could simply do is, because this force is a constant force and the displacement here is also some constant value, the work done that we kind of described in class in general for a constant force, I'm going to kind of write that as a subscript, the constant force, the scalar product of the constant force times its displacement, which we have described in class as delta L. In this particular case, that's going to be equal to the force that we have, F, and the displacement D. Okay, so we're going to simply write down what those quantities are. That's 210 newtons in the I-hat direction, plus 150 newtons. I'm sorry, that's not plus, that's minus 150 newtons in the J-hat direction. And the scalar product of that vector with the displacement vector of 15 meters in the I-hat direction, minus 12 meters in the J-hat direction. So kind of like we showed in class, that we can actually take the components of these, we multiply just like you might do in 8th grade or 9th grade algebra, where you multiply the outside, the first, the last, the outsides, and the insides. Well, if we were to write out all of those quantities, we would see that the first quantities, the two quantities here in front, would give us 210 newtons times 15 meters, and that would be I-hat dotted into I-hat. And then the last terms would give us a quantity, so we want to add that. It would give a quantity of minus 150 newtons times minus 12 meters, and that would be J-hat dotted into J-hat. And then the other terms, without even writing them out, so we would add to that two other terms. There would be two quantities here that would be I-hat dotted into J-hat, plus another two terms here of J-hat dotted into I-hat, right? The scalar product of J-hat and I-hat and J-hat, which kind of asks the question of how much of J-hat is in the direction of I-hat. Well, when J-hat describes the unit vector in the y direction and I-hat describes the unit vector in the x direction, we know that these two are perpendicular to each other. So these will both give us 0. And likewise, these, because they're completely in the same direction, J-hat, the scalar product of J-hat and J-hat, and the scalar product of I-hat and I-hat, are in the same direction, these just give us a value of 1 each. And so we simply can add up the numbers that we get left over, right? So this is going to be 210 newtons, simply times, we don't even need to write the dot product so carefully, times 15 meters, and then this is minus 150 newtons times minus 12 meters. This is really just going to be plus 150 newtons times 12 meters. And I'll leave it to you to figure out the final steps of those two questions, of actually multiplying these through and summing them up. Right? We're going to get units of work. Right? The units of our answer, we can clearly see, will be newtons times meters. In both cases, we have newtons times meters. And so the units will definitely be newton meters, which we talked about in class as being joules. Right? So we know we're getting an energy, which is what we would expect to get for work, and we would simply add up these two quantities. I hope that's helpful.